So let's welcome the fourth presentation given by the Lin Fang Gao.
Hello everyone, my name is Lin Fang Gao. I'm a PhD student in the Department of Machine Engineering at Stanford University, and under the supervision of my PhD. And this project, we call it geometry-driven design of mobile surface structures by using topology optimization and circle packing. And this project we have been collaborating with some mathematicians from the Department of Mathematics and Computer Science, and also Toyota Research Institute of North America. Okay, so the outline of my today's presentation will have 5 parts. First off, I would like to talk about the motivation background, and then design movable surface structures, shape and topology optimization of complex mechanism, and computational result and verification, and references. Okay, so first of all, let's talk about the motivation background. So movable surface structures have gained significant attention in recent years due to their ability to transform into various shapes. It can be like applied in many engineering fields like acoustic surface, software robotics, and architecture and medical applications. And it also has very great potential application. For example, the animation shown here, which is NASA aircraft wing morphing, so it can be morphed into the desired shapes. But how to design a mobile surface structure is quite challenging because the challenge is due to the complexity of the interplay between the material properties, structural mechanics, and desired shape transformation. For example, how can we design and control the moving behavior, and how can we just how the surface morphing and how much it's going to morphing? That's quite challenging. So to address these challenges, we propose novel frameworks that integrates computational conformal geometry and topology optimization for the design of more surface structures. So that's what we call geometry-driven design of more surface structures using topology optimization and circle packing. Well, we can start with this picture shown here, which is from the flat panel to the hemisphere, and it is covered by the circle packs. So we leverage the circle packing to model the moving behavior, and then conformal mapping is employed to deform the circle pack surface between 2D to 3D configurations. Well, the angles are well preserved. For example, for conformal mapping, we know when, for example, the picture shown here, from the initial shape to the target surface, so angle and shape are preserved, but area and size are not preserved. So that's a characteristic of the conformal mapping. And the circle packing theory is a powerful tool for computational conformal geometry, so that enables representation of surface using collection of the circles. So we can start with this first example. That's a very interesting example. So we know the conformal mapping, the angle and shape are well preserved, but the area and size are not preserved. For example, if we have the human face, and if we just map it to the unit disk conformally, that means the shape are well preserved. So we can see this example here. But if we just cover this unit disk by using a texture image, and then pull back to the human face, to the face surface, so the conformal mapping are directly visualized. So if the texture image is a checkerboard texture, which is shown here, and we just cover this unit disk by using the checkerboard texture image, and then pull back, we can see the result shown here. So the angle and shape are well preserved, but size and area not preserved. So which means from unit disk, there's a checkerboard, and to the human face, there's still a checkerboard. And if we just replace this checkerboard by using the circle packing, so what will happen? We can say this picture shown here. From unit disk, there's a circle, and to the human face, there's still a circle. So what is changed? The only thing changed is just the radius of these circles. So this can significantly reduce the complexity of the design movable surface structure. And by using this conformal mapping and the circle packings, we can transfer the overall surface morphing problem into a local radius change of the circle packs. And the movable surface design problem can be recast as a circular accurated design problem. And after that, we're going to design the movable surface structures. So back to this very simple example. Well, we have the circle packs from the flat panel to hemisphere. So we want to design a kind of mechanism that can be expanded radially in radial direction. So which is shown here, which means the circle becoming bigger, right? So based on this idea, so we have the design, which is rigid body mechanism. So that's what we call expansion pulley. By rotating this big gear here, and we can control the expansion rate in radial direction. But we feel like if we just design this kind of rigid body mechanism, well, we can achieve the rate of change of the subsystem. But how are we going to control and how are we going to model this curvature of the overall surface? That's quite challenging. So here we have the idea, which is we said double layer mechanism affects the overall surface structure curvature. Sorry. So the idea is if we can just add a cover at the top layer, so which means we want upper layer expand a lot and the lower layer expand a little. So with the interaction with different circles, where it can create the curvature. Yeah, and based on this idea, we have the double layer expansion pulley. So it seems like we already found the solution, but we feel like maybe it's better we can try to use a compound mechanism. The reason why we choose compound mechanism because they're advantage of the flexibility, adaptability, lightweight, simplified design, and ease of manufacturing. So can we just design a compound mechanism that has the two layers? The upper layer can expand a lot, and the lower layer can expand a little. So here we are going to use the shape and topology optimization of the compound mechanism. So what is topology optimization, which is a numerical tool that optimizes the best material layout within a given design domain. And the method we're going to use for topology optimization is the left-hand method, which uses a higher dimensional function to represent the 2D design domain. And we can see this phi is a left-hand function. When it's larger than 0, it means the material domain, and when it's equal to 0, that represents the boundary, and less than 0 is represent the void. And the advantage of the left-hand method is because it ensures a clear boundary, which can provide a precision and optimization accuracy improve, and easy to handle the topological change. And the evolution of the boundary dynamics governed by the Hamilton-Jacobian equation, which is shown here. Sorry. And Bn is the design velocity, can be determined by the sensitivity analysis. Okay, so back to our problem formulation. We want designing a mechanism that has two layers. Upper layer expand more and lower layer expand less. So here's our boundary condition of the single piece actuator. So we have the force input from the left top, and we have the roller constraint at the left side, and the fixed constraint at lower bottom. And these two blue squares, which represent the kinematic region, and these two red squares means the target position. Okay, so back to our problem formulation. So this design problem can formulate into two objective functions. The first one is the minimize the spiral of the actual displacement field and the target displacement field. And the second objective function is load carrying capability, which is maximize the overall surface stiffness, which is minimize the compliance of this overall surface, overall structures, while in the meanwhile maintaining the prescribed volume ratio. And this design problem is subjected by the AUV to LV, which means AUV is the energy by linear form, and LV is load linear form, and U is our state variable, and omega is our design variable. So we can see here the schematic of general boundary condition. So this problem can be formulated as a PDE constraint problem, because we have the Dirichlet boundary condition, Newman boundary condition, and Vn the design velocity acting on the boundary of the surface. Okay, so here we are going to use the Lagrange multiplier method, so which we can transfer the PD constraint problem into an unconstrained problem. So the L is a Lagrange function, and the J is our object function, AUV minus LV, which means the governing equation, and we have the Lagrange multiplier. And after that, we're going to do the total derivative of this Lagrange function, and then we're going to apply the adjoint variable method. So after that, we can get the final design velocity which is shown here, and we're going to put it back to our Hamilton-Jacobian equation, because the evolution of the evolution of the boundary dynamics governed by the Hamilton-Jacobian equation. Okay, so here's our design example. So this one is the animation of our evolution, you can say it total to like 2,000 iterations, and that's the final result here. So the boundary condition for reference here, and that's a convergence plot. And the volume ratio we give you is 30%, and it total take 2,000 iterations. And now we're going to talk about the computational result and verification. So we have the boundary condition for reference and the final result, and we're going to do the final analysis, which is for verification. So we can say from this example, so we can see there's two target kinematic target, and they just moving in different direction. No, in different rates. So that's what we're trying to design. We're trying to design a two-layer mechanism. It can expand and also affect the overall curvature. So we just extrude a little bit and revolve in a circular direction. So here the circular symbol mechanism, so it's like the face hugger in the moving area. Right? And that's the section view, and that's the final element analysis validation, and that's the animation. We're going to apply the force here and fix at the bottom. Okay. So each of the circular mechanism represent each circles in the circle packing. Well, if we just cover surrounded by a cylindrical wall, so we'll do the verification again. And here is the transformation of the flat surface to a complex 3D geometric through the circle packing based workflow design. So you can hear each of the circles can be represented by each of the circular mechanism, and that's a single circular compliant actuator corresponding to the circle packing structures. Yeah, and our contribution in the project, we propose a novel approach that uses conformal geometry to control the surface morphing and circle packing, and by using the circle packing and direct receive flow. And this approach offers a systematic way to define and achieve specific morphing behavior while preserving the angle with the geometry integrity. We have developed a streamlined, precise, combined conformal geometry model with logic optimization, and it allows this kind of integration allows us to generate design for single piece morpho surface structure automatically, and we also opens up a new possibility that enables creation of complex and precise morpho structures. Yeah, that's the reference. Yeah.
Okay.
Thank you. Question and comments.
Any question or comment? All right, I think that's a very interesting
Yes.
research. And can you move back to the previous slide?
This one?
Yeah, I think we'll be interested to evaluate the stiffness of your structure, I mean the configuration.
Yes.
Yeah.
Well, you can see from this picture here, it generated by the conformal mapping and the circle packing is initially used in computer graphics. So they don't care about this thickness. So what we are trying to design, the very thinner complex mechanism that can also expand in radial direction and also can affect the overall curvature. So that we're trying to design, and we're trying to make it as thinner as we can.
Okay. And
hope I answered your question.
Yeah, you did. And I think you developed a methodology to optimize the configuration of your design, right?
Yes.
Do you try any other method to verify your design, or the result of your optimization is correct, or that is the optimal?
Actually, we didn't do any experiment. Yeah, because we're focused on the computational design. So yeah, it'll be better if we can do some experiment. Well, definitely in the future work. Yeah. Yes, please.
So the conformal mappings,
Yes.
is that more so, are you using that because like more so there's a lot of pre-existing theory you can leverage?
Yes.
Or is it more because there's like a physical reason? So like if angles locally change going from one surface to another
Yes.
from like just the design problem point of view. Is that okay?
Yeah, that's okay. Well, actually, we can see here from the base surface to the unit disk. So, well, the conformal mapping is based on the triangulation, which is the match of the surface, right? Which means the angle are not changed. So that the people say, oh, okay, that means the angle should preserve, but the average size not preserved. From this example, you can see here. So the reason why we are choosing circle pattern is because the circle, the only change is just the radius of each circle. So it's easier for us, for engineers, to design a multiple surface structure because the only thing changes is just radius. Yeah, we just follow the direction of the circle pattern. Yeah.
All right. Any other question, comment? Nothing? Okay, that's it. Thank you.
Thank you.
So let's welcome the last presentation.